Hi, my name is Kowalski.
My name is Stokes.
And our senior project is conversion from a carburetor to a fuel injection system on a 1953 Chevy 3100 pickup. Now, our project background here, we're using a 1953 Chevy 3100 pickup, and the engine will be a 401 Buick Nailhead. Now, the 401 Buick Nailhead was only made from 1959 to 1966. And with this engine and such a short lifespan, there are not many aftermarket parts which we were able to use for this project, which we'll see later on was part of a difficult consideration we had to go through to find the pieces we needed.
Alright, so the main challenges that came with the Buick 401 Nailhead, mostly as Frank has stated, is that due to its limited production run, there aren't very many aftermarket supports for it. It's not your average Chevy 350 RS motor, which there are a lot of. So the limited quantity run and the limited production number limits the amount of designs and current aftermarket parts there are for it. The other challenges with it were the original manifold is a carbureted dual plane manifold. Those are very difficult to work with, especially if you're trying to adapt a fuel injection system for something that doesn't have a perfect pre-made aftermarket kit for it. So just the way the runners are designed, they aren't evenly proportioned. Some sit higher than others. Plus, it's also a cast manifold, which is a difficult material to machine and work with.
Now, for parts available for this system, as I said earlier, it's an older engine and a very short lifespan, so there weren't many aftermarket parts. So we needed to find electronic fuel injection computers and sensors, regulators, all these different components that would work with our system that we were going to use for our intake manifold, and they would be compatible with this system. They'd be able to be tuned and properly tuned so that we could have the required or desired horsepower and efficiency out of the engine that we wanted. The throttle body, we also needed to find one that would fit our needs and be able to have the proper size to fit under the engine and in the plenum that we were designing. And fuel injectors as well, we needed to find the proper fuel injectors with the required pound-hour fuel injection rate that would run our engine without starving it for fuel.
Alright, so the main benefits that come with a port fuel injection system or any type of fuel injection system in general is mostly it's better power and a lot more reliability. You've ever driven a carbureted car, they don't like to start on cold mornings. You have to usually have a automatic choke, or in this case, the manifold itself had pre-drilled pilot holes that allowed exhaust heat to fill the manifold to be able to make it easier to start on a cold day, which isn't very efficient. Carburetor is also very hard to tune unless you know what you're doing. You have to know pretty much exactly how it works, know which screws change your throttle, how wide your throttle blade opens, excuse me, how much fuel gets into the engine, how it idles. And if you don't know what you're doing and you don't know all the intricate parts of the carburetor itself, it makes it very hard to tune, and you can oftentimes will lose power and reliability. With the multi-port fuel injection, it'll be a turnkey system. It won't have any difficulty starting on cold days. It'll fire every single time. The fuel injection also will provide more power and a lot more ease of tunability with the programmable ECM. And more power will come from the fact that just injecting the fuel straight into the cylinder is more efficient than atomizing it using a carburetor through the plant.
Now, our project goals here are mainly to, one, increase the fuel economy of the truck. Now, with the old carburetor, it wasn't as efficient as, say, a modern fuel injection system. So with the new fuel injection system, we're hoping to increase the fuel economy of this vehicle, and through tuning and testing, we will determine the new fuel economy with our new system installed on this vehicle. Another goal is to increase the overall drivability of the vehicle. As Spencer said, with an old carburetor, cold mornings, they don't like to start as much, it's not as responsive, it's not as efficient of a system. With a modern fuel injection, it'll always start, you'll always have the response you want, it'll be more efficient as it's injecting fuel straight into the cylinder instead of running through a carburetor and being atomized as the older system was. And thirdly, the increased horsepower of the engine. This will give the engine slightly more power with a more modern system placed on it, more modern technology. We'll be able to tune it with the electronic control module through the electronic fuel injection system to monitor and change what we'd like about the system.
Alright, so our deliverables for this project is that we, due to the difficulty of working with the stock dual plane intake manifold, part of our deliverables is that we are going to be designing and building our own custom intake manifold. Probably going to be using a material, aluminum material, probably 6061. We also have to design this manifold in SolidWorks and test it to make sure that test it using flow simulations to make sure that it will flow an adequate amount of air. The velocities of the air coming in aren't too strong or too weak. There's no really stagnant or pooling spots. There's no really obstruction to the air coming into the cylinder, flowing around the, coming into the plenum, flowing around the plenum and then going down the runners as the intake valve is open on each cylinder. We also are going to have to calculate the size of our throttle body. In this application, we're actually going to be using two throttle bodies because the two sides of the engine are going to be split between two different plenums. So we have to do the accurate calculations to make sure that those throttle bodies will allow enough air when at wide open throttle or at idle to make sure that the engine runs properly. We're also going to have to size our fuel delivery system. Being an EFI setup, you need to use an electronic fuel pump. The Buick 401 came with a mechanical fuel pump. We're going to be not using that and using a inline electric fuel pump that will be outside of the tank with a filter, and we have to make sure that fuel pump will provide enough pressure to the injectors to be able to run the injectors properly and make sure that they dispense the correct amount of fuel when triggered. The other thing we're going to have to do is make sure that the ECU, the programmable ECU, is fully wired and run in the truck. Back to what I was saying about the dual throttle bodies, the other concern we're going to have to make sure that we do is we're going to have to make sure that the two throttle bodies themselves will open simultaneously, because if they do not open simultaneously, one side of the engine will run either leaner or richer than the other, and that can lead to mechanical issues and possibly catastrophic failure. So we have to make sure that the throttle bodies open simultaneously to allow equal amounts of air to be distributed to the engine.
So design considerations to keep in mind. First one being that we need to design our new intake to accept modern day fuel injection parts. As I said, there are not many aftermarket parts for the old 401 Buick Nailhead, so we're going to be using modern day injectors, fuel rails, sensors, and we have to design our intake manifold with enough room and space to implement all these parts. The runners need spots for the fuel injectors to be placed in. There needs to be room above to connect the fuel rail to all of them. The sensors need spots to be placed onto the engine in certain areas, and those areas will be determined, and we must keep in mind where they are and allow enough room to place those sensors in later on. Now, the size of the engine bay, being an old truck as it is, there was a lot of room under the hood. but we still have to keep in mind different components under the hood and their placement of them in regards to our intakes. We must make sure, for instance, on the right side of the engine will be the master cylinder for the brakes. We have to make sure our intake is not too big as it would hit the master cylinder. We must make sure there's enough clearance in between so that it's not in the way of the master cylinder or any other components around the engine. Lastly, as Spencer just said, we have to design a system that will simultaneously open both throttle bodies on either plenum at the same time, at the same rate, so that they both have the same exact flow through them. And we'll simply come up with a design that one throttle body opens, the other one will actually open at the same rate as that one, most likely with a rod connecting the two in between the intakes.
This is our initial intake design. This is just a very rough design based on guess calculations on approximate size and proportions. The most accurate part of this drawing here is the base flange. The base flange is based off of the actual intake flange, so that is accurate representation of those dimensions. So the design is going to be changed considerably from here. Our main concerns are with the runners. With being square tube, we don't know if we're going to have the capability to be able to properly bend the square tube. The other concern was the size of the plenum itself. It's a little bit big, a little bit bulky, and it's going to be hard to try to duplicate to make sure that it is perfectly symmetrical with the other. A good idea we have about that right now is we might be switching the shape of the plenum itself from a box to almost a larger tube. Another design consideration after talking to our stakeholder was we have talked about merging all of the runners into a more neutral center point, so that way you don't have to worry about flow going to one end of the plenum and making sure that seeing that some of the runners will get more than the other. So, as I said, this is the initial design. The final design will be a little bit more to the stakeholders' liking, and it'll look a little bit more sleek and refined.
Now, for the intake design considerations, as Spencer said, the intake plenum may need to be sized differently. At this moment, we made it just as a general size to fit the throttle body that we had. So possibly we will bring down the size of this to make it a little bit smaller to allow for room for different components on the engine. It's possible also that we may change the design of the plenum itself from the box shape as it is right now to a round tube. Now, for this, we just need to consider the fact that the throttle body and the bolt holes on the throttle body itself must fit within the inner diameter of the tube so that we can make a plate that we can weld onto the end of the tube that can attach the throttle body so that it all fits in one. And with this, there'll be much more even flow throughout the plenum. It will flow more evenly to the runners. It's a consideration we're keeping in mind right now, and we'll possibly change our design to this shape later on. Now, the calculations for this system, there are a few of them, and these are just some of the basic ones here. The first one being the size of the throttle body. Now, the size of the throttle body is measured in cubic feet per minute of air. So that equation is maximum RPM times volumetric efficiency times the displacement over the constant of 3,456, and this is all multiplied by the constant of 1.7. So for our engine, we're going to have a maximum RPM of 4,400 with a volumetric efficiency of 0.8 and the displacement of 401, as it's a 401 cubic inch engine. And this is divided by the constant of 3,456 and multiplied by 1.7 gives us a CFM of 694. And with 2 throttle bodies, we'll easily be able to reach a necessary flow rate for these plenums, being 694 cubic feet per minute. And the next one will be the fuel pump size. So the fuel pump size is measured in gallons per hour, how many gallons of fuel the pump will bring to the engine per hour. And this equation is simple. It's target horsepower over 10.5. And our target horsepower is the horsepower of the engine at the moment, which is 325 over the constant of 10.5, which gives us a rate of 30.95 gallons per hour, which we'll look for a fuel pump possibly slightly larger than this, as to ensure that under load there will be no worry that the engine will starve for fuel. Finally, the fuel injector sizing. Now this is measured in the injector flow rate, how much fuel each injector injects into the cylinder when it's fired. So this is a simple equation of target horsepower over brake-specific fuel consumption, multiplied by brake-specific fuel consumption, and this is divided by the duty cycle over the number of injectors. So the horsepower will be 325. The BSFC is 0.5 pounds per horsepower hour, and this is divided by the duty cycle of 0.85 times the number of cylinders, 8 cylinders, and this gives us 23.89 pound-hours for the fuel injectors. Now it's allowable, it's accepted to use a fuel injector 50% larger than what is calculated here. Therefore, we're going to be using fuel injectors that are rated for 26 pound-hours off of an old Ford. They're Bosch injectors.
Some of the hurdles we're going to have to face with this project, as mentioned before, we have some minor spatial concerns, mostly with the height of the manifold. We actually have to make sure we cannot make it too short. That is based off the design of the engine. Being that it's a Nailhead engine, the head cover, the valve covers, sit vertical instead of following the angle of the V as they would on, say, a Chevy 350 or an LS motor. So due to this, when you take off the valve covers, you're going to have to lift them straight up and over the edge of the rockers. So we have to make sure that we do not make our plenum too short, or else it won't allow us to lift the valve covers off and be able to service the valves if need be. The other concern we're going to have to consider is how we're going to fabricate our plenum. Aluminum itself is not a very hard material to work with. The most difficult part about working with aluminum is welding it. Welding aluminum is almost exclusively TIG welding. That is a little bit more intense and extensive version of metallurgy and more forms of melding two different pieces of metal. So probably over the winter break, probably Frank and I are both going to take TIG welding classes, so we're going to be able to weld our own plenum together and not have to rely on an outside source.
Lastly, here we have to make sure there's enough room for all the sensors and ejectors on our intake manifolds. We must make sure the clearances are enough between the intake and the runners so that we can fit all the components we need into our system. And our parts list here, we're going to be needing, as of right now, a fast, easy EFI system. This is the electronic control module that will control all of our components. 2 throttle bodies from a 3.1 liter Chevy engine, which is what we're going to be using on either of our plenums. Our 8 fuel injectors running at 26 pound-hours. GM temperatures and sensors, map sensors and TPS sensors, throttle position sensors. And finally, the fast, easy EFI fuel pump and regulator for our fuel pump system to regulate the fuel into the engine. All these parts are the main components we need in order to make this system work. This is our works cited page. Thank you.
Thank you.